In exercise 927, we're going to be doing halohydrin formation. So we're adding some sort of a halogen. They say predict the major product that you expect when you treat each of the following alkenes with a halogen and water. The halogen and hydro, water, gives you a halohydrin. So here we're going to be forming these halohydrins. Now the notes we want to remember about it are the notes that we explained in the concepts behind this reaction in the previous video. The OH and the bromine will add on opposite sides of the double bond. They will add anti to each other. If the OH is coming out, the bromine will be going away. If the OH is going away, the bromine will be coming out. That's the first thing. And second, the OH is going to attach to the more substituted carbon. And that's because the water is attacking as a nucleophile. It's attacking the bromonium ion, and it's going to attack the more substituted carbon because that's the carbon that can handle having the slight positive charge, as we drew and talked about in that previous video. Okay, so first step, you see an alkene and instantly you should think, I can do an addition reaction with this, as opposed to substitution or elimination. They're telling us to draw what you get when you treat this with bromine, molecular bromine, and H2O. So we see a halogen, we see water, so we're going to be halohydrin formation. So redraw the original molecule just without the pi bond. Look at each of the two carbons in the double bond. We need to know which one is more substituted. The one on the left is bonded to 2 carbons, so it's secondary. The one on the right is bonded to 3, so it's tertiary. So we're going to add a bromine to the less substituted carbon and the water to the more substituted carbon. Furthermore, we're going to add them anti. So the bromine will go on the less substituted secondary carbon. If I draw it coming out, then when I draw the more substituted OH, it will have to be going in the opposite direction, namely pointing away. Now, we want to make sure that these are tetrahedral, so if an atom has 4 bonds drawn explicitly, 2 of them need to be in the plane, 1's going away, and the other one needs to be coming out. So we'll modify this so that this is coming out, and we have the other carbon there. So that's one of our products, but because the original molecule that we had to work with, the alkene, was flat, each of the carbons in the double bond are trigonal planar, because that's flat, these can react with either side. There's no preference for one side over the other. And so you end up getting a racemic mixture of the 2 enantiomers. Now to get the other enantiomer, just take any bond and switch its configuration. So if bromine is coming out, then we're going to have it going away in this enantiomer. If the OH is going away, we're going to have it coming out in the enantiomer. If the ethyl group is coming out, we're going to have it going away in the enantiomer. And so those are the two, you get a racemic 50-50 mixture of those 2 products. If you did halohydrin formation, you added a halogen and water to this alkene. Okay. Next, what if we treated this with those same reagents? Molecular bromine and water. So you'd see the double bond, you'd think, okay, an alkene, I have a pi bond. That means I can do addition reactions, as opposed to substitution or elimination. What am I adding? You look at the recipe, you're adding a halogen and water. So you'd redraw the carbon skeleton exactly as it is, just without the pi bond. You're going to use those extra electrons, that extra molecular glue, to stick new stuff onto this molecule. We're going to add a bromine and an OH, a Br and OH. The OH goes on the more substituted carbon. So of these 2 atoms in the double bond, the one on the left is tertiary and the one on the right is secondary. The one on the left is bonded to 3 carbons, the one on the right is bonded to just 2. So the OH will go on the more substituted tertiary carbon, and the Br will go on the less substituted carbon. Okay. Now that's one thing, knowing what we're adding and where we're putting it. But second, we have to know the directions that it faces in. So we have to know that these are going to be anti, So if the OH is coming out at us, then the Br would have to be going away. And there's no reason why the OH would just be coming out. It could have just as well added to the opposite side of this flat double bond. So if it's going away from us, then the bromine would be coming out. And so those are the two products that you would get in a racemic mixture of halohydrin formation with this alkene. And the one other thing is you want to make sure that those bonds, if all four bonds are drawn explicitly, you want to make sure that they are drawn as tetrahedral. So here, for example, we have one bond out of the plane, two in the plane, the other one should be going away. So this methyl group should really be going away. Same thing with the bottom one. If we have two in the plane and one going away, the methyl group should really be coming out. In the case of the bromine, we don't have to worry about that because all four bonds are not drawn explicitly. So it's understood that the hydrogen would have the opposite configuration, the one that we need in order to get a tetrahedral shape. So those are the two molecules you would get if you did halohydrin formation with the structure, the alkene, they gave you in B. For C, yet again, they want to know what we would get if we treated this with molecular bromine and water. So you'd see an alkene, you'd look at the alkene, you'd say, okay, I'm going to do an addition reaction, as opposed to substitution or elimination. Pi bonds are signals that you can do addition. What are you adding? You'd look at the recipe. We're adding a halogen and water, hydro. So it's going to be halohydrin formation. Redraw the molecule exactly as it was, just without the pi bond. We're going to use that molecular glue to stick new stuff onto the molecule. The molecular glue that is pi electrons. Now, the OH is, so we're going to add Br and OH. The OH is going to go on the more substituted carbon. So of these two carbons in the double bond, the one on the left, that's bonded to two other carbons, so it's secondary. The one on the right is just bonded to one other carbon, so it's primary. The OH goes on the more substituted carbon, so that'll go on the secondary carbon, and the Br will go on the other one. Now, so far we've recognized what we're adding and where we're adding it. But then we have to think about the three-dimensional orientation, how it added. These are adding anti. So the OH, if that's coming out at us, then the Br would have to be going away. Now this is a chiral center here, and so in that chiral center, there's no reason for you to get one enantiomer over another. The alkene, the double bond is flat. The carbons in it are trigonal planar, and so these reagents can react with either side with equal probability. And so you won't just get the one enantiomer, you will also get the other, where the stereochemistry of each of the bonds switches. If it was pointing out at you, then it goes away. If it was going away, then it can point out at you. So you'd have a 50-50 racemic mixture of those two enantiomers if you did halohydrin formation, adding a halogen and water to this alkene. Okay, with D. So D, they're asking us what would happen if you treated this with molecular bromine, Br2, and water, H2O. Well, you'd see the alkene, you'd say, well, we're definitely going to be doing an addition reaction as opposed to substitution or elimination. We're going to use that extra molecular glue to add something onto this molecule. So redraw the structure just without those pi electrons. We're going to use those pi electrons to stick a new thing on here. What are we going to add on? Well, you'd look at the recipe. You'd see a halogen, you'd see water, you'd think, okay, this is halohydrin formation. I'm adding Br and OH. Now the OH should go on the more substituted carbon. If you look at the two carbons in this double bond, they're both secondary. They're both bonded to two other carbons. So it doesn't matter where you put the OH and where you put the Br, because neither is more substituted. So if you have the OH on top coming out at you, then the bromine on the bottom would have to be going away because they add anti to each other. There's no specific reason it would only add that way. You could just as well have it add in the opposite direction. The OH could be going away, and the Br could be coming out. They do have to add anti to each other, though. So these are the only two ways that those can add on that molecule. And so if you did halohydrin formation with this alkene, if you added a halogen, molecular halogen, and water with that alkene, you would end up with a racemic 50-50 mixture of those two enantiomers. So hopefully this gave you some help with how to approach synthesis problems that ask about halohydrin formation.